Okay, well, see, if I want to just calculate tau without the arrow, I can say that tau equals 6 centimeters times 0.05 newtons, which is 0.003 meter newtons. Okay, I can make that calculation. That's the magnitude of your torque. But if I want the vector torque, well, I've got to include the sign and everything. Well, I do this product, this 6 centimeters that I got from this calculation, and multiply it by the 0.05 newtons, the force. And then I know from the right-hand rule that that torque has to be in the negative k direction. Into the board, that's the negative z direction, so it's parallel to the vector negative k. So I can write the vector torque just by multiplying the magnitude by negative k. Okay? Now, when I say magnitude, let's be a little bit careful. I don't really get a magnitude here because if this angle happens to be between 90 and 270 degrees, I'm going to get a negative sign, and I need to hang on to that negative sign. That negative sign comes right through here and gets multiplied by this. Okay. Okay, in any case, that's what we get. And then we multiply it out, we get 0.003 meter newtons times negative k. Now, I'll comment, I did say this in class, it's kind of worth looking at these videos sometimes, that I call this a meter newton, not a newton meter. And that's to distinguish it from a joule. Because, you know, a meter times a newton is the same as a newton times a meter, and a newton times a meter is a joule when you're doing a calculation for energy, but when you're doing calculation for torque, it turns out to have exactly the same units, but it means something different. So to distinguish, we don't call this a joule. We never call this a joule. We call it a meter newton. Now your textbook will probably call it a newton meter. That's okay. But I recommend that you use meter newton just to make sure you don't confuse it with the unit of energy. Okay. At the side, we see that then the acceleration is the torque over the moment of inertia. Well, if I divide this by the moment of inertia, which is 0.001 kilogram meter squared, I get 3 radians per second squared, and that's still times the negative k. Then we ask, well, what's the change in omega in the next tenth of a second? Well, let's assume that tau doesn't change, because obviously as the wheel moves one way or the other, the angle is going to change, so our perpendicular is going to change, so your torque is going to change, so your angular acceleration is going to by darn change. Well, we're just going to make the rough approximation that the torque doesn't change. It does, it will in the next tenth of a second, and it will change somewhat significantly. So we don't really take this approximation too awfully seriously until we analyze the uncertainties and the error in the approximation. But we're going to assume that the torque doesn't change. Well then, how do you get a change in velocity? You multiply acceleration by a time interval. That's the definition of acceleration. So assuming that you have a constant acceleration, which results from your constant torque, which isn't really the case, but we're pretending it is, we multiply the angular acceleration by delta t, and that's going to give you the change in the angular velocity. So your delta omega is going to be alpha delta t, and that's a straightforward calculation. We said delta t is a tenth of a second, so that, and I didn't write that on the board, it was on the paper we were working from, but if delta t is a tenth of a second, actually there it is, it's on the board, and the tenth of a second, we multiply that by the 3 radian per second squared, and we get 0.3 radians per second. And that's still times negative k. So your change in omega is in this direction. Even though your rotation's in this plane, your omega is out of the plane for reasons we've talked about. Okay? Well, then, if the omega was initially 4 radians per second, in the counterclockwise direction, Okay, well, the counterclockwise direction is this direction, and by the right-hand rule, the other part of the right-hand rule, you can curl your fingers in the direction of motion, your thumb points in the direction of that vector. Okay, so that's the positive z-axis, that's out of the board. So that the omega naught is 4 radians per second times your k vector. So that omega f is omega naught plus delta omega. That's your 4 radians per second times k, added to your negative 0.3 radians per second times k. Okay? Now put the negative in front of the 0.3 instead of the k, but certainly that's valid. Okay. So we get 3.7 radians per second times k. So now we know what the approximate change in velocity is. Okay? And we know then the approximate final velocity. Now we'll comment that as you move out here, your torque is going to get bigger because as this vector goes this way, its x component gets bigger, right? So actually it's probably going to be 10 or 15% bigger. So you'll have 10 or 15%, but on the average is going to get 10 or 15% bigger. On the average is probably going to be 10% bigger or less. So you might have something closer to 0.32 radians per second. That would be my, off the top of my head, estimate of the average torque. So, check my estimate if you want. It's an interesting calculation. You're going to have to do something like that sometime. And so, this isn't totally accurate. It might be closer to 3.68 or 67 radians per second, but this is still going to be a fairly good approximation. Okay, so based on this estimate, what's your delta KE? Okay? Well, it's going to be your 1/2 I omega F squared minus your 1/2 I omega naught squared. Everybody knows the formula for kinetic energy, because in a somewhat unusual approach, that's what we developed first. We developed the moment of inertia by calculating kinetic energy of a hoop. Okay, well anyhow, that's what we have. And we do that calculation. I think you come out with negative 0.001 joules. I've got a question mark after that. Check it out yourself. Here's I, and here are your 2 omegas. Square the omegas and do the difference. I think this one comes out something like, now let me be careful about that. I might have one too many zeros on that. Okay, no, I don't think I do. Okay, if I square 4, I get about 16. If I square 3.7, I get about 14. So the difference here is going to be about 2 radians squared per second squared. If I take half of that, I get 1 radian squared per second squared. Half of the difference in the omega F squared, and multiply that by I think I still say I'm going to get about negative 0.001 joule. And I say negative because, yeah, this is less than this. And also because this thing is, well, most directly, I was going to say this thing is slowing down and do all that, but the most direct way you can see this is that this force is being exerted against the tendency of the wheel to rise. So if you go to the definition of kinetic energy, you find that the force is doing work in the direction opposite the y displacement. And that's what we're going to use in a minute. Okay, well, whether we understand that or not, we will in a minute. Okay, so, and you might well understand it. Okay, well, very simple calculation, kinetic energy change. Your change in angular position is what? Just the average omega times delta t. Now we've assumed that tau doesn't change, so since the moment of inertia doesn't change, alpha doesn't change. Since alpha doesn't change, it means, at least with our approximation, that we have uniform angular acceleration. which means that your omega versus t is linear, which means that your average omega is the average of your initial and final omega. That's an idea you want to keep repeating to yourself and get into your head. It's kind of a profound idea, and it's an idea that you can then modify when you have a slightly nonlinear situation. Okay, well, I hope you think about that. But more immediate things to think about. Okay, how do we calculate average velocity? Well, we average the initial and final. Now people say, okay, you add them together and divide by 2. Sure, that works. That's fine. That's a good way to write it down. But look at these two numbers. What's the average of these two numbers? 3.7 and 4. You should be able to do that mentally. Okay? It's halfway between here and here. Well, between here and here, the difference is 0.3. Halfway between, the difference is going to be half of 0.3, which is 0.15, which means it's going to be 3.7 plus 0.15, 3.85. Now, you should be able to look at these numbers and immediately see you got 3.85, and if you can't, either, potentially you might have just trouble doing calculations mentally. Some people do, and some mathematicians do, and some engineers do. It's not a totally disabling handicap, but most of us can pretty easily do that calculation if we just think through our calculations rather than immediately running to the calculator. And you should always estimate what your calculation is going to give you before you run to your calculator, because if you press the wrong button and believe what you see, you're in big trouble. Okay? You got to have an idea. You should always estimate. And in this case, the estimate is easy to do exactly. We get to 3.85 radian per second average velocity, multiply that by delta t, times k, because we're doing the vectors, right? And we get 0.385 radians times k, which is like 20 degrees times k. So our angular displacement, our angle changes by 20 degrees in this direction, right? But if you want that angular change represented as a vector, the vector's got to be perpendicular to the plane. And that seems a little weird, I know, and it is until you get used to it. But that's about 20 degrees then times k. Okay, I think 0.385 radians is reasonably close to 20 degrees. Okay, so that's how we calculate the displacement. Then, I think I said calculate the change in potential energy. I just want to check the time on this video because it's getting a little bit long, and I do want to stop and then pick that up after a short interruption.